Hello, dear students. I hope all of you are fine. As we all were doing D block elements, in this video I will be continuing with that. And we will cover the remaining properties of D block elements, which are magnetic properties, and then formation of colored ions, then formation of complex compounds, after that catalytic properties, formation of interstitial compounds, and alloy formation. So in order to start today's video, the first property that I am going to discuss is magnetic properties of transition elements. See, as it is written in the slide, when a magnetic field is applied to a substances, mainly two types of behaviors are observed. Okay. One is diamagnetic, the other is paramagnetic behavior. So whenever a magnetic field is applied to substance, two types of magnetic behavior are observed. One is diamagnetic, the other is paramagnetic behavior. Dia and paramagnetic. Now what is it? Diamagnetic substances are repelled by the applied field. Diamagnetic substances are repelled by the applied field, and paramagnetic substances are attracted by the magnetic field, as it is written. Okay, now to add to these, you must know that the substances which are repelled by applied field have no unpaired electrons in them. Okay, so the diamagnetic substances have no unpaired electron in them. Now the other one, paramagnetic substances which are attracted by the magnetic field have unpaired electrons in them. Have unpaired electrons. Okay. Now suppose the number of unpaired electrons will decide the magnitude of paramagnetic substances. What does this means? This means that more the number of unpaired electrons, more will be the paramagnetic behavior, which we measure in the form of magnetic moment. Okay, the paramagnetic behavior is measured in the form of magnetic moment. Right? See, it is written that the magnetic moment of any transition element or its compound ion is given by, the formula is given, mu s is equal to under root n plus 2, where n is the number of unpaired electrons. To understand it more clearly, you must know that paramagnetic arises due to the presence of unpaired electron. Okay, now the magnetic moment is associated with spin angular momentum and orbital angular momentum. So the magnetic moment that we calculate can be represented as mu total. Okay, can be represented as mu total, and this is equal to the sum of spin angular momentum and orbital angular momentum, which can be represented as mu s plus mu orbital. Okay, orbital, right? So in order to calculate the magnetic moment of paramagnetic substance, mu total is equal to mu s plus mu orbital. Mu s stands for spin angular momentum and this stands for orbital angular momentum. Now, if we see only the first series of transition elements, the contribution of orbital angular momentum is suppressed. Okay. Now if we talk about the first series of transition metals, the contribution of orbital angular momentum is suppressed. This one. So what is left? Only this one. So we can ignore this orbital momentum since it is of no significance. So we can say that the magnetic moment is determined by only spin only formula. Okay. So now we can write that this magnetic moment is calculated by mu s, and the formula is written here. Mu s is equal to under root n plus 2. Okay. The formula is written mu s is equal to under root n plus 2. Fine. And the unit is known as Bm, which stands for Bohr magneton. The unit is known as Bm, which stands for Bohr magneton. Right? Okay, students. So we can write that mu s is equal to under root n plus 2. Fine. The unit is Bm, Bohr magneton. Now, as I told you, this n stands for number of unpaired electrons, and one more thing that you must know that more the number of unpaired electrons, more will be the magnetic moment. Okay, more will be the magnetic moment. More the number of unpaired electrons, more will be the magnetic moment. Fine. Now let us go through an example. Suppose if it is asked that we have to calculate the magnetic moment of divalent ion in aqueous solution if its atomic number is 25. It is given that the atomic number is 25. Now if I write the configuration, what will I write? Ar 3d5 4s2. Now according to the question, we have to calculate the magnetic moment of the divalent ion. Okay, we have to calculate the magnetic moment of divalent ion. Now suppose if M changes into M2 plus, then only it will form divalent ion. Now the configuration will be what? Ar 3d5. Fine. Now the number of unpaired electrons will be how much? It will be 5. Since it is 3d5, the number of unpaired electrons will be 5. Now if we substitute this value in the formula, mu will be equal to under root 5 plus 2. Now when you solve this, you will get the answer as 5.92 bm. Right? Okay. I hope this is clear to you. So first we will calculate the number of unpaired electrons and then we will substitute in the formula and we will get the answer. Now one thing that you will observe that whatever will be the number of electrons, suppose as in this case, the number of electrons were 5. So whenever you solve this 5 plus 2, okay, whenever you will solve this, you will get something 5 point something. Okay, what is the value of n? That much value you will get before decimal and you will get something after decimal. So if I have n is equal to 4, then my answer will be what? Something 4 point. Okay, like 90 or whatever. Now if the number of unpaired electrons are 1, suppose, My answer will be 1 point something. This you have to remember. So in this way, this value or this value indirectly tells us about the number of unpaired electrons present in that metal. Okay. Now you have understood that magnetic behavior can be of two types, either diamagnetic or paramagnetic. Diamagnetic behavior is shown when all the electrons are paired, and paramagnetic behavior is shown when either one or more than one unpaired electrons are present in that metal ion. Now you must be aware about one more term which is known as ferromagnetism. Okay, you must have studied about this ferromagnetism. What is ferromagnetism? Ferromagnetism is an extreme form of paramagnetism. Okay, ferromagnetism is an extreme form of paramagnetism. Okay, substances which are attracted very strongly are known as ferromagnetic substances. Okay, substances which are attracted very strongly are known as ferromagnetic substances, and it is an extreme case of paramagnetism. Fine. So you must now remember this, that many of the transition metal ions are paramagnetic in nature, and the formula used to calculate the magnetic moment is, again I am repeating, under root n plus 2. What else you have to remember? That more the number of unpaired electrons, more will be the magnetic moment or more will be the paramagnetic behavior. Okay. Now this way, this property is completed, magnetic properties. Now we will move on to another property, which is formation of colored ions. Okay. Formation of colored ions. So the question is asked that why do transition elements form colored ions? One basic thing that you need to remember is the word DD transition, DD electronic transition. So if the question asks why do transition elements form colored ions, what you will write? You will write due to DD transition. Now what is it? I will explain it to you. What is DD transition? Now see children, first let us see the slide once. What is written in that? See, it is written that the absorption of visible light is due to DD transition. Okay. That is an electron jumping from a lower 3D orbital to a higher 3D orbital. Now, in order to understand it more clearly, see, I will explain it to you that whenever there is an isolated gaseous atom, okay, whenever there is an isolated gaseous atom of a transition elements, all the d orbitals, all the d orbitals are degenerate. All the five d orbitals are degenerate, which means that they are equivalent in energy. Fine. So what is the name given to these orbitals? You know it, dxy, dyz, dzx, dx square minus y square, and dz square. Now, if I talk about isolated atom or ion of a transition elements, or all the 5d orbitals are of same energy, or we can say that they are degenerate. Now, under the influence of ligands, now what are these ligands? This you will study in coordination, or you have studied about this in coordination chapter, that ligands, when ligands approach then what happens? This degeneracy is lifted and these orbitals split into different sets. Okay, these orbitals split in two different sets. Now if I talk particularly about octahedral field, then this will split in two sets in which three orbitals will come with lower energy and two will have higher energy. These three orbitals are dxy, dyz and dzx, and the above two are dx square minus y square and dz square. Dx square minus y square and dz square, these have higher energy because these are on the axis. Okay, these are on the axis, and the other three are between the axis. Okay, these three are between the axis. Fine. So I hope it is clear to you that when ligand approach to form the coordination compound, then the degeneracy of these d orbital is lifted and they split into two sets in octahedral field. The lower set is known as